Hi scholars, welcome. Mr. Hinkle here to share about numerical dating, a big leap forward in the development of our geological timescale and our understanding for the age of the Earth. It all comes down to this quantitative method of dating geologic substances, in particular rocks and the minerals that form these rocks. This new technique in the 1800s called radioisotopic dating was developed that could establish time units for various rocks. Now, this is a beautiful complement to relative age dating, which was in its heyday in the 16th, 17th, 18th, 19th centuries. Now we're getting up to the 19th and 20th, and we're bringing new technologies. Absolute age dates corresponding to relative age dates, and it's looking at what is called radioactive decay of the elements that make up the rocks. If you remember, rocks are made of minerals. Minerals must be naturally occurring, solid, inorganic, with a definite chemical composition and a crystalline structure. So that chemical composition is the chemistry. Zoomed out. Elements are earth materials. They're matter. Now, elements are made of atoms, the smallest unit of matter that cannot be divided. Atoms are made of subatomic particles. Protons, neutrons, electrons, the protons and the neutrons inside of the nucleus. The amount of protons in the nucleus define how or what element it is. We've got P's, we've got N's, and we've got electrons. Now the number of protons, that's the atomic number. So every hydrogen has one proton in its nucleus. Every carbon has 14 protons in its nucleus. Now we have what are called isotopes. They are different versions of elements with different amounts of neutrons, right? So we've got carbon-12, 6 and 6. We've got carbon-13, 6 and 7. Carbon-14, 6 and 8. In fact, I think I read this wrong earlier. Carbon doesn't have 14, it has 6. My mistake. It happens, but I'm going to roll with it. So carbon has 6 protons in its nucleus. 6, 6, 6. It stays the same. Carbon-12 has 6 neutrons. Carbon-13 has 7 neutrons. Carbon-14 has 8 neutrons. These are called isotopes of carbon. Now, isotopes are important for calculating numerical ages. It goes like this. Most isotopes stay. So you've got protons and neutrons inside of this nucleus, and for as long as time occurs, this is stable. But certain elements have certain isotopes that decay over time. This is called radioactive decay. As time goes on, the isotopes change into another form. At the time of formation, it's 0% daughter, 100% parent. And so that means that the rock cools and it solidifies and it's all the same. But as time goes on, radioactive decay occurs. And there's this concept called a half-life. The amount of time that it takes for 50% of the original material to change. 50% of the parent to change to the daughter. So after one half-life, we're 50-50. And then that 50% goes to 25%. So at 2 half-lives, we're 25%, 75%. Another half-life, You guessed it. Now we're going to be at 12.5%, 87.5%, because it's that half of 25%, which is 12.5%. So, numbers, figures, what the heck is going on? Certain isotopes in rocks break down over time according to a specific time scale, according to radioactive decay. So here it is, magma, really hot, start time, it's all parent, 1 half-life, 50-50, 2 half-lives, 75-25. We are looking at the decay constant of the parent, and basically the way that this happens, right, okay, I'll go that in a second. I find a rock now, and we grind that rock up and we put it through a mass spectrometer and we record the relative abundance of parent to daughter. And for many isotopes, uranium, lead, potassium, carbon, we know the decay rate. Knowing the decay rate and observing the relative proportion of mother to daughter atoms inside of a sample allows us to calculate the age of that rock. So it is through this method by which we can, with confidence, say the Earth is this old, this is the oldest evidence of life, this is how old these events happened, the impact that quite possibly led to the extinction of the dinosaurs occurred 65 million years ago. How do we know that? Radioactive age dating of the layers of rock that surround the iridium covering the entire planet. So for recent ages, we can use carbon dating. Carbon dating is a radioactive, radioisotopic age dating technique, but it looks at using organic materials. So we can only use it for recent time periods because as time goes on, organic material decays and is preserved in the rock record and the carbon no longer becomes useful. The decay rate is really, really fast. So carbon from the atmosphere gets into carbon in the plants, gets into carbon in the animals, which becomes carbon in the soil, which can be preserved for short periods of time. So numerical age dating is the complement to relative age dating, whereby we can use radioactive decay of specific isotopes to put actual numerical or absolute ages on rocks. And this is wildly important because understanding how old rocks are really helps us understand how old is the Earth, how old is the universe, and how old is everything. This is numerical age dating. Thank you.